In this pre-calculus algebra video, we'll look at quadratic functions and their graphs. To start with, here's an idea of what we're looking at in this section. In many sports, involve throwing an object, kicking or hitting it, but we see an object like this basketball being projected. One of my favorites, and I'll leave this for you to look up, is pumpkin chunkin. I know it's a real thing. Look it up. Look up their website and see that. But you see these massive machines that are just throwing a pumpkin, and these are national competitions. And you can see that it's the same path. You use the same math to calculate that projectile, that pumpkin's trail of how it's projected. But in this section of the textbook, we're going to learn to use graphs of quadratic functions to gain a visual understanding of some of these projectile sports and other things. Here's some essentials that I'm going to encourage you to pause the video and jot down. These are just absolute essentials. There's not a lot here, but 3 things, really. It's just 3. 3 things that you want to really firmly know and understand. The first, we've got the quadratic formula. That's old news, right? Oh, I hope it's old news. You should know that by now. If you don't know it yet, please make time now to memorize this quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. If you need some help with that memory work, try going to YouTube and just search videos on the quadratic formula. You'll see all kinds of crazy songs that people have created to help you learn that. But it's really essential at this point. If you don't know that yet, you really need to commit that formula to memory. Now, here's how we're going to use that formula here in this unit. So knowing that was old news, but let's look at the formula for just a minute. And if you were to get rid of, now this isn't a very politically correct term I'm going to use, so I hope I don't hurt anyone's feelings, but we're going to get rid of the ugly part of this formula. If you were to pick out, okay, here's the part that I think is the most ugly, the most challenging to deal with, would you agree with me that it's going to be this radical? So what if we just get rid of that radical, the ugly part? We don't tell anyone I said ugly. Okay, there we go. If we get rid of that radical, what are you left with? The opposite of b over 2a. That in itself, that opposite of b over 2a, is going to be a really important formula to use to find the vertex of a quadratic equation. So the graph of a quadratic equation gives us a parabola. Here's an example of a basic quadratic equation, and it gives us a parabola. This point in the parabola, the low point, or if it's a downward opening parabola, the high point, is called the vertex. And the x-coordinate of that vertex can be found by getting rid of this radical in the quadratic formula. So we get x equals the opposite of b over 2a. Now, once we have x, you can then find y by simply replacing x, or plugging in that x that you got, the opposite of b over 2a, into the function, and that'll give you y. So we'll have an x and a y coordinate for the vertex of this parabola. So that's the second essential. The third essential is just to understand this, that just to know when you see an equation of a parabola, that a positive parabola smiles. That's this one. So a parabola that's positive opens upward like a smile. The negative parabola, so if we have a negative out in front of it, opens downward like a frown. If you can remember that, we've got a positive parabola smiling, a negative parabola frowning. There you go. So if you could remember those essentials, that's going to help you throughout this unit. Let's bring some of those things forward and apply them. True or false, the vertex of a parabola is always the minimum point of the parabola. Well, if we're opening upward, a positive parabola, then yes, the vertex would be the minimum. But what about these parabolas that open downward, the negative parabola, like f of x equals the opposite of x squared? Now that vertex isn't a minimum, it's a maximum, right? So I'm going to call this one false. Can you graph this quadratic function, f of x equals x minus 4 squared minus 1? Sure you can. I don't think you'll have any trouble with that. Let me show you how to do that. I've got some steps here stored away underneath there. This is taken right out of your textbook. You could pause the video to jot these down. Really important steps that could help you each time you're going to do this problem. But the key here is to use the vertex. And when we've got a graph of a quadratic equation, we're not even, so in this form, we're not even going to need to use that vertex formula. You could do this. We could find a, b, and c. We'd have to multiply this out to get x squared minus 8x plus 16 minus 1, so x squared minus 8x plus 15. So we could multiply this out and then find what a and b are. But even easier, in this format, the vertex is just handed to us on a silver platter. The x component of the vertex is going to be 4, and the y component of the vertex is going to be -1. Did you see that the 4, it's x minus 4, but that means that this moves 4, if we're using transformations, that means that that would move 4 to the right, correct? And that -1 means that we're going to move down 1 unit. So the vertex is going to be at +4, -1. And then once we have that vertex, we could replace x with 0 to find another point. But let's start by graphing that vertex 4, 1. The vertex 4, 1, x equals 4, y equals 1. Here's our vertex. Now also, did you notice that this is going to open upward? Because we start out positive, we know that we're going to open upward. So we know that from this vertex we're going in a positive direction. And then next, if we find f of 0, that's easy. We just go to the equation and replace x with 0. So we'd have f of 0 equals the, it's a positive, right? We determined, excuse me, f of 0 equals 0 minus 4 quantity squared minus 1. I think I was copying the example over here. Sorry about that. So f of 0 equals the quantity of 0 minus 4 quantity squared minus 1. And if we simplify that, we'd get -4 times -4 is 16, and 16 minus 1 is 15. So we have this second point that when x is 0, y will be 15. When x is 0, y is 15. So that's going to be off of our chart slightly. 11, 12, 13, maybe about here. if we continued this chart, we could call that 15. And because parabolas are symmetric, I can see that if I went 1, 2, 3, 4 units left, I went up to 15. So if I go 4 units right, 1, 2, 3, 4, I'm going to have this other point here. And there we've got 3 points of our parabola, and we could continue graphing it. So it looks something like this. It's not a very pretty graph. I apologize for that. But you could see the points are clear. Let's look at another example. This isn't in your notes, but just to be clear, what do you do when you get a parabola, a quadratic, that's not written in vertex form? So did you see this one was nice because it was written in vertex form. It handed us our H and our K, our vertex, on a silver platter. Here it was, H was 4, K was -1. If that doesn't come to you so easily, then we can still graph it. We're just going to have to find the vertex using this formula. So let's look at this example. If f of x is the opposite of x squared minus 2x plus 1, and this one wasn't printed in your notes, but I'd encourage you to write it. So this one is negative, so it's opening downward, right? It's frowning. Down, frown. I know right off the bat that it's going to look like this. And if I find the opposite of b over 2a, the opposite of b is 2, and a is -1. So in this form of the equation, we've got a equals -1, b is -2, c is 1. So if I replace b with if I replace b with -2, but we have the opposite of -2, that's why I wrote it as a +2, and 2 times -1, I'd get -1, and once I have that x, I can find the y component, right? So I could find f of -1 equals the opposite of -1 squared minus 2 times -1 plus 1. So I'm going to go into the function here and just replace every x with a -1. Be careful here. Do you see how I've modeled this? I just did the opposite of parentheses squared minus 2 parentheses plus 1. Simple step. I just replaced each x with empty parentheses, and then with a different color, I'm going to go in and fill in the -1. -1 squared, -1 times -1 is +1. So it looks like we'd have, this negative is still here. So the opposite of +1, -2 times -1 is +2 plus 1 gives us a 2. So it looks like the vertex is going to be -1, 2, right about here. And then step 3, I could find when f of x equals 0, I can find the x-intercept. So if f of x is 0, I'm going to set the equation. I'm going to set f of x to 0. So I'd have 0 equals the opposite of x squared minus 2x plus 1. And when I do that and use the quadratic formula, I get 2 approximations for the x-intercepts. So I could go ahead and plot those in. X-intercepts of -4/10, so right around here somewhere, and -2 point something right around here. So I know I'm crossing the x-axis at those 2 points, and then I can find the y-intercept. If I go into the equation and replace each of the x's with 0, then I'd get 1. So the y-intercept is 1. Let me do that with a different color here. When x is 0, y is 1, so we've got this point. So now we have, in blue, we have the y-intercepts, and in red, we've got the x-intercepts, right? And that gives us plenty of information to be able to sketch the graph here. So it looks something like that. So there's another example when the equation is in the form ax squared plus bx plus c when it's not in vertex form. Let's keep plugging along here. Consider this quadratic function. Determine without graphing whether the function has a minimum or maximum. Well, back to our positive and negative parabolas, this one happens to be a negative parabola, right? And here's why it's negative. It starts out, the x squared has a coefficient that's negative. So this is a negative parabola, and negative parabolas frown, opens downward. So this one we know is going to open downward. If it's opening downward like a frown, that vertex, is it a high point or a low point? Is it a minimum, a low, or a maximum, a high? That's going to be a maximum. So we know we can start by determining without even graphing that this parabola, this quadratic function, is a maximum point. And now we can find that maximum point by evaluating the opposite of b over 2a. Using that vertex formula, and again, if you didn't learn this yet, we're going to go to the quadratic formula and just scratch out that radical, and you get the opposite of b over 2a. X equals the opposite of b over 2a, so that's if a is negative 4, b is 8, and c is negative 3, then that's the opposite of 8 over 2 times negative 4, which gives us 1. Now if I replace x with 1, I could find f of 1. Negative 4 times 1 plus 8 minus 3 gives us 1. So it looks like the vertex is at x equals 1, y equals 1. I'm going to use a different color for this y so we can see this. So when we answer this question, find the minimum value. The minimum value is the y value, that one. The minimum value is 1. Where does it occur? Where it occurs is the x value, the green one. And then we can identify the domain and range. Well, if I did picture this, we're at 1, 1 for the vertex, and we know that it's opening down. I'm not going to bother about finding any specifics, just that it's frowning and it's starting here at 1, 1. Then what I can see is that the domain is all real numbers because it's quadratic, so there's no restrictions in the domain. But the range, I can see we stop at a positive 1. You could go as low as you want because it continues to go down and down and down, but the highest y value is a 1, and I'm going to put a bracket around that 1 because 1 is included. So the range would be negative infinity to 1. Let's look at one last example here. Quick word problem application. Among all pairs of the numbers whose sum is 16, find a pair whose product is as large as possible. What's the maximum product? I have here a step-by-step, 5 steps that you can follow. Pulled that right out of your textbook. You might want to stop and jot that down in your notes. That could be really helpful to you if you need to. Pause the video for a minute. But when I look at the steps, number 1, read the problem carefully and decide what is being maximized. I have it right here. Among all pairs of numbers whose sum is 16, what's the maximum product, right? What do we want to maximize? The product. So use the conditions of the problem to express the quantity of a function in one variable where that product is what we want a formula for. So if the product is a times b, these two numbers multiplied by each other, then if I let a be one of those numbers, then I can use this fact that a plus b equals 16 to find the other number, because if a plus b is 16, then b would be 16 minus a. So if one number is a, then the other number is 16 minus a. Now if I rewrite this with a f of x notation, so in other words, let me go back to this. If I called the ax, then the second term, the second number would be 16 minus x. I could write their product as x times 16 minus x. And that's the hard part of the problem. Now, if I simplify this, if I multiply this out, I can get this in a form to find the vertex. If I distribute that x, I'd get 16x minus x squared, or if I rearrange it, put the square term first, the opposite of x squared plus 16. So a, the coefficient of x squared, is -1, b is 16. If I replace those values in for x equals the opposite of b over 2a, remember where that comes from? Just get rid of the radical from the quadratic formula, and I've got the opposite of b over 2a. So the opposite of 16 over 2 times -1. So -16 over -2, or 8. Looks like x equals 8. So the two numbers are, one of them's 8, and now I could find the other number, because the other number is 16 minus 8. So it looks like that other number is 8 also. So the last step, I could answer the question. The question says, find a pair of numbers. And so I can answer the question by saying, therefore, the two numbers are 8 and 8. Practice that type of example a few times. Just in wrapping it up, here's those essentials again. We start with the quadratic formula. You've got to know that. And if you do know that and you scratch out the radical, we've got the formula to find the x component of the vertex, which is the opposite of b over 2a. Once we have x, we can plug that into our equation to get the y value of the vertex. But being able to find the vertex is very, very beneficial when working with quadratics. And then the other thing to remember, essential, is remembering that positive parabolas smile. So x squared is upward opening. There's a positive. And the opposite of x squared, a negative parabola, is frowning. So that'll wrap up our work in this unit. If you have questions about the content, please don't hesitate to contact me or jot it down in your notes and we can discuss in class.